something like 10 problems due. And I mean, at the end of the day, it's worth 25%, okay? 25, okay guys, we're gonna lower our voices a bit. So it's worth 25%. I don't think you have a homework percentage as high in your other math courses, right? Am I right or not? No. So I mean, you have to do homework every week. 25%. Oops. Okay. So every week you will have homework due. There is even the midterm week. You will have homework due. That's not. You know, that's something that I will not change. So, yes? September 13th. Okay? So, 3 days after Agile. The one after is due on 20th, 27th, and so on. Okay? Yeah? Yes. You can do it the way you want. Okay? Just, I mean, as long as you can talk to each other, you can discuss it with me, and you have the power of the internet. But as long as you don't violate the academic integrity rules, I have, you know, I mean, you know, who can tell if people, but anyways, I mean, you know. Again, so a lot of the problems, so I'm thinking of something that on the midterm, there will be at least a problem from the homeworks that is not graded, okay? So I will not be able to grade all the homework, but one of the problems that I won't be graded will be on the midterm, okay? So that way I will encourage you to do them all. Now for the midterm, I need to finalize the date. The last possible day I have is Wednesday, October 30. Are we good? During class. Everything is during class. Do you have any other math midterms? What do you have? Analysis? Okay, well, I mean, I booked it first. So, okay, so October 30th is going to be the midterm. Yes? No, it's in class time. It's during class. It's right now. Yes. Pardon me? Yes, of course. I mean, solution is already written. Okay, so yes. It's going to last 1 hour. Yeah? Are we like angry at this or? Yeah. It's going to last 1 hour. I will write for approximately 40 minutes maybe. So you have 10 extra minutes. Okay? Any other thing? Yes? Yes?
It's just about the tutorials.
Tutorials start today.
And at what time? Yeah.
Check Minerva. Yes? Pardon me? I mean, I said I'll open the crowd mark after Tuesday. On Wednesday it will be open. Okay, Wednesday morning I hope to have it open. Yes? Wednesday, October 30. Pardon me? Sorry. Sorry?
Calculus 3 is on Wednesday after.
That's okay. You can write 2 midterms in 1 day. Okay? Just to suppose it's on Monday 27, on Monday 28, and then study for it, and then write it on 30. That's okay.
Wait, so when is it?
Okay?
When is it?
Yes? No, there are 3 sections, I think. There are 3 TAs. Okay, great. Let's get started. So last time we were doing functions. We were studying functions. And now we will talk about inverses of functions. So let S be a set. And let 1S or IDS, this is identity basically, identity on S, be the function x and s. Basically, you just map everything to the same thing, right? Of course, this is a bijection, right? You see that? Yeah, this is bijective. Okay. So let f from a to b be a function. We say that g from b to a is an inverse. Is an inverse. For now, it's an inverse of f. If f composed with g and g composed with f, so f of g of b, so it's the identity on b, and g of f is the identity on a. This means that f of g of b is equal to b for all b in b, and g of f of a is equal to a for all a in a. Okay?
Sorry.
Yes?
You just write a little bit bigger.
Yeah, okay, thanks. I'll do my best. Okay, are we good? So f. Okay, is it clear here?
Can you
Let's-
actually write that part bigger, because it's hard to see.
This one?
Yeah.
This one here?
Just go
Okay,
back.
so
Can
f
you write it?
of g of b is equal to b for all b and b. Is that right? Is that good? And g of f of a is equal to a for all a. Okay? Clear? Yes?
And the first one, is it 1s?
1s, 1 sub s. Okay, just a symbol. Have you seen this symbol before? No. Okay, this means a function that sends everything to the same thing. So on the real line, it's f of x equal x, just a diagonal line, right? This is a function. Okay, are we good here? Yeah?
No.
Yeah. Any question? 1s, is this notation confusing? 1s? Is it confusing you, the notation? Okay, so what is 1s from R? What is 1s from R to R? It's a function that sends x to x. That's it. 1s is a function that sends any element to itself. Yes?
What's the identity on this?
Yeah, we call it the identity on S. On S.
So 1s is the same as the
IDS, yeah, exactly. 1S, IDS, we'll be using these. Okay?
Okay, thank you.
Great. Okay. I mean, let's give an example here. I mean, we know this example from calculus. So consider f from 0 infinity to r that sends x to log of x, and then g from r to 0 infinity that sends y to e of y. You know that these are inverses of each other, right? Yeah? How do you check that they're inverses of each other? So you look at f of g of y. What is that equal to? This is just ln of e of y. Everything makes sense, right? Because e of y is a strictly positive number, and you get y. And you look at g of f of x. Well, what is that? This is e of ln of x. Just ln x. Okay? This is just a generalization of this thing. Are we good here? Is it clear? Okay. Any questions? Any questions? Are we good? Great.
Wait, can you raise it back up?
Pardon me?
Can you raise it back up? I didn't finish writing the bottom.
Okay. Oh, you're type. Okay. Yeah. Well.
That's
Pardon?
no the one on the bottom.
Yeah. This one?
Yes.
Okay. Good. Sorry. Okay, are we good? Now, when does a function have an inverse? Yes? When it's bijective, right? Have we seen this theorem before? Well, now we'll see it. So let f from a to b be a function. Then the following are equivalent. So I'll be writing the following are equivalent. F is bijective. And 2 F as an inverse. Okay? These two things are equivalent. I'll prove one of these two statements and let you do the other as an exercise. Okay, so I'll prove, let's say, I'll prove 2 implies 1. Okay? I'll prove 2 implies 1, and as an exercise, you'll have to do 1 implies 2. Okay? Deal? So let's do that. 2 implies 1. Suppose that f has an inverse. So let G from B to A be an inverse of F. So far we're using an inverse, but technically it's the inverse. There's only one inverse, and I think that's a problem in your homework, right? In your homework you have to show that the inverse is unique. So let G from B to A be an inverse of F. Okay. What do we need to show now? We need to show that F is bijective. That F is bijective. What does it mean bijective?
Both injective and surjective.
That F is surjective, is injective, and surjective. Are we good here? Everybody? Any question? Any question? Any question? Okay, which one do you want to start with? Let's start with injectivity. F is injective. So to show F is injective, what do I need to show? Yes?
For two of the same input, you get that two of the same input. No, sorry. Then the same output implies the same output.
Exactly. So let A1 and A2 be in A. This is how you should be writing your proofs. Let A1 and A2 be in A, such that f of A1 is equal to f of A2. What do we need to show here? I need to show that, everyone, what do I need to show?
A1 is equal to A2.
I need to show that A1 is equal to A2, right? Great. Now I have f of A1 is equal to f of A2. Now f of A1 is in what set? F of A1. B. Everybody, are we good? F of A2 is in what set?
B.
Now what function can I apply from B to A?
G.
G, right? Agreed?
Yes.
So G of f of A1 is equal to G of f of A2. Are we good here? Yes? Now what is G of f of A1? This is G composed with f. I mean, I'll do one extra step, that's okay. So it's G composed with f at A1 is equal to G composed with f at A2. Now what is G composed with f?
It's just that.
It's just the identity on what set? A. It's just the identity on A of A1 is equal to the identity on A2. Now what is the identity of A on A1? What do you get back? A1. And then here what do you get back? A2. Okay, so f is injective. Are we good here? Any question? Great. Now we will show that f is surjective. Okay. So what do I need to show when I say I need to show f is surjective? Someone else? Yeah?
For all elements of B, there exists an element A, such that F of A.
Exactly. So let B be in B. We need to find A in A such that f of A is equal to B. Isn't that right? That's what surjectivity means. Okay, let me see if I can pull this work. Yeah. that's- Okay. Okay. How do I start? So I have B in B. Now, what's one of the only things you can do to something in B? Yeah?
Well, you could either go from G.
Exactly. So let B be in B. B is in B. So G of B, where does it belong? In what set? Everybody? A. Great. Now, what is f of G of B? Let's hope we get lucky. What's f of G of B? This is f composed with G at B. Agree? Now, what is f composed with G? This is the identity on B, which is B. Oh, wait a second. I have that f of G of B is equal to B. G of B is in A. If I let this little thing be A, if I let A equal G of B, what is f of A? Okay? I've shown that f is surjective. Are we good here? Any question? Yeah? Great. Let's move on. Okay, now we'll do a theorem. I'll say the theorem. I think this is a theorem you have to prove in the homework. Theorem. Let f from A to B be a function, be a bijective function. Then the inverse of f is unique. Okay? If you have two inverses of f, then they must be equal. Okay? We write, and the inverse, we denote it by f inverse. Okay? It's just notation. Okay? Great. I think you have another question as well. I think I put two questions on that. They're both not too hard. Yes, sir.
So like when you're grading the homework and like you're not gonna check all of the questions, are you gonna do it by exercise or by some
Please try
exercise?
not to because it's taking the whole book. Just a second. Yeah. Yeah.
Like, are you checking by like entire exercises or like by?
No. I might ask for parts to be graded.
Okay.
I might say part 1, part 2, grade part 1, grade part 2.
Okay.
Again, there are 220 students, and I'm trying to do my best to get the grades after 1 week. Okay.
Okay. Thank you.
It's yeah, it's a bit tough. Okay. Any questions on this? Awesome. Okay, now let's move on to equivalence relations. I think this is something that might be new. Have you guys seen this before, equivalence relations? This is, I think, the first new thing that you'll see in the course. Equivalence relations. Any question on this stuff before? Yes?
What does it mean that f is unique?
G is unique. The inverse of f is unique. So basically, if, very good question, if G from B to A and H from B to A are inverses of f, then G is equal to H. Okay? Are we good here? Yeah, oh, by the way, there's something I need to sort out, is office hours. So office hours, I'll have 3 hours per week. So I was thinking Tuesday, Thursday, and Friday. Is that okay, so that you can see me every day, and Friday there's the homework due, if anything, okay? And what do you prefer, in the afternoon or in the morning? Afternoon. Let's say after class time, like 5 to 6 or something like that, 4 to 5? 5 to, okay, who prefers 4 to 5? 5 to 6. Okay, so I guess on Tuesday it will be 5 to 6, and on Thursday it will be 4 to 5, and I'll let you know on Friday, okay? Okay. So I mean it's, yeah, I mean if you need to see me, you can see me every day. Where are we now? Equivalence classes. Okay, equivalence relations. Okay, so let X be a set. I don't know, I think I put a problem on this as well. Oh, by the way, everybody knows matrices, right?
Yeah.
We have seen matrices.
Yeah.
We know what a vector space is.
Yes.
We know what a subspace is.
Yes.
Okay, great. Awesome. Okay, so let X be a set. A relation, an equivalence relation on X is a subset R of X cross X with the following properties. Okay? Now, could you give me a particular subset R from X cross X? We've seen something like that satisfies some properties. A function from X to X, isn't it a subset of X cross X? Yeah? You remember this? A function from X cross X, a function from X to X is a subset of X cross X with a particular property, right? Remember this? Yeah? Okay. With the following properties. A, the pair for all x in X, if X is in X, then XX belongs to R. This is called reflexive. Reflexivity. Forget it every time when these are 12. Now if X and Y are in X, and what? If X and y are in X, xy belongs to R implies that yx belongs to R. See? This is called symmetry. Symmetry. If xyz are in X, then xy belongs to R, yz belongs to R, implies xz belongs to R. This is called transitivity. Okay? Well, this is something maybe new, but it's not very bad. Okay, it's not as bad as it looks. Okay, is it clear? It's just a subset of x cross x with these properties. No more, no less. Okay? We say that x is related to y if xy belongs to y. Yes?
Okay, I'm actually a bit lost with the x cross x.
Yeah. What is x cross x? It's the pairs.
Coefficient.
So you have x, you have x, right? It's just the pair AB, where A is in A is in x, and B is in x. Right? What is R squared? You know R squared, the plane? It's a pair of coordinates. The first one is in R, the second one is in R. Same thing here. It's a pair of coordinates. The first one is in x, the second one is in x. Is that clear, everyone?
Yes.
Okay? Well, coordinates, I don't mean like, yeah, okay. But it's just, yeah. Okay?
Cartesian problem.
Yeah, it's a Cartesian product. We've seen this, right? We've seen it. Yeah, okay.
Just before seeing what are functions.
Yeah, okay, yeah, because for functions we need Cartesian products, right? Okay, thanks. Okay, great. That's it. This is an equivalence relation. It satisfies three properties: reflexivity, symmetry, and transitivity. And we say that x is related to y if xy belongs to this magical subset of x cross x. No more, no less. Now, let's give an equivalence relation. Example. Let x be a set. Say that x is related to y if, let's say, x is equal to y. Define a relation as follows. Say that x is related to y if x is equal y. Related, just a word, right? X is related to y if x is equal to y. Now I need to check that this is an equivalence relation. Yes? Yes, yes. Let x and y be in x. Thank you. Let x and y be in x, and say that x is related to y if x is equal to y. Is this relation reflexive?
Yes.
Is x related to x?
Yes.
Reflexivity. Is x related to x? Well, let x be an x. Can I say that x is equal to x?
Yes.
Yes.
Everybody, can I say x is equal to x?
Yes.
x is equal to x, so x is related to x. That's it. Are we good? Great. Symmetry. If x is related to y, is y related to x? Well, if x is related to y, what can I say? Then x is equal to y. Does this mean that y is equal to x? Then y is equal to x. Are we good? Then y is related to x. Are we good here? Great. What as well? Symmetry, transitivity. If x is related to y, and y is related to z, is x related to z? Well, let's see. X related to y, what does it mean? X related to y implies that x is equal to y. Y is related to z implies that y is equal to z. Does that imply that x is equal to z or not? Everyone? X is equal to z, which implies that x is related to z. Are we good here? Are we good? Awesome. Let's do another one. Let's do another equivalence relation that is slightly more complicated, but not that much. Any questions on this one? Yeah.
Just a question, like whenever we have like these questions, you just gotta like prove three
You
things.
you just have to go through these properties. Exactly. Yes.
In this case, this R is the x, y.
Very good. That's the next point. What is R?
Is it real numbers?
Pardon me?
Is that what it is? Like is R all the numbers?
No. Well, xy belongs to R if and only if it's so R in this case. Well, let me write this down. R in this case, what will it be? It will just be the set of pair xx as x belongs to x. It will be xy such that y is equal to x. You see that? So I mean, let me write this down. R in this case is going to be the set of pair xy such that y is equal to x. Which is going to be the set xx as x. Okay? So if x is z, basically you have 1, 1, 2, 2, 3, 3, 4, 4, minus 1, minus 1. Right? That's a good question. Okay? This is R in this case. Any question? Great. Let's define another relation. I'll try to pick, let's pick the number 3 and say, let x is equal to z, and let xy be in z. Say that x related to y if, let's say, if x minus y is divisible by 3. Is this relation an equivalence relation?
X minus y?
X minus y is divisible by 3.
No.
So let's see. A, is it reflexive? Is x related to x?
Yes.
What is x minus x?
0.
0. X minus x is equal to 0, which is divisible by 3, right? Yes or no?
Yes.
Yeah. Divisible by 3. So x is equal to x. Now symmetry. If x is related to y, is y related to x? So if x is related to y, implies that y minus x is divisible. Sorry for the people in the back. Implies that y minus x is divisible by 3. Sorry, implies what? Oh, x minus y, sorry. X minus y is divisible by 3. Does it imply that y minus x is divisible by 3?
Yes.
6 is divisible by 3. Is minus 6 divisible by 3?
Yes.
9 is divisible by 3. Is minus 9 divisible by 3?
Yeah.
Yeah, it implies that y minus x is divisible by 3. Divisible by 3, which implies that y is related to x. Okay? Are we good here, guys? Yeah? Any questions? Easy work, right? It's not, well, it can get a bit tough, but in general, for now, it's going to be as simple as that. Okay, transitivity. Transitivity. If x is related to y, and y is related to z, is x related to z? Let's see. If x is related to y, what does it mean? It means that, what does it mean? If x is related to y, yes?
Means that x minus y divisible by 3, so you can say like
Yeah?
x minus y equals 3k for some k.
Exactly. Are we good here?
Yes.
X minus y is divisible by 3 means that x minus y is equal to 3k for some k in z. Are we good here? Everybody? Yeah? Now, y is related to z. What does it mean? Along the same lines. Anyone can help? Anyone can help? Any new person? Yes?
That means y minus z equals to 3 times some L.
Yeah. Give me a number.
Right?
Yeah.
Yeah.
What? Give me a letter. L.
Uh,
Yeah, that's okay. Y minus 3z is equal to 3L for some L in z. Isn't that right? Now, how I get to x minus z? Yes?
Well, we can do x minus y plus y minus.
Exactly. Very good. So x minus z, let me put y, insert a y in between. This is perfectly fine, right? What do I get? It's 3k plus 3l. Well, let me factor a 3 out. This is 3k plus l. K plus l is an integer. So is x minus z divisible by 3?
Yeah.
So x minus z is divisible. By 3. So x is related to z. Okay? Now maybe I want to help you a bit. I think I've asked a question on the homework. I did not say show that this is an equivalence relation. I said, is this an equivalence relation? To my memory, I believe both are. Okay? So the answer should be yes to both questions. Okay? Are we good here? Yes?
For example, and when you ask us, is this, we always have to prove our answers.
Yeah, exactly. Yeah. It's not yes, right? I mean, it is yes, but you have to show your work. Yes.
Can you show an example that is not an equivalent?
Yeah, sure. That's on your next homework. Okay. Okay. But I mean, I can show something that is on equivalence. Yes.
So every time you have to go like this,
Yeah.
then like this.
Exactly. You have to show reflexivity, symmetry, and transitivity.
Yeah.
Okay. Now, is there a relation that is not an equivalence relation? Let's try to think.
Bigger than.
Less than.
Bigger than, less than, right? So define a relation on Z as your friend suggested. X is related to Y if X is strictly bigger than Y. Okay? Is this reflexive? Is X strictly bigger than X?
No.
No. So this is not an equivalence relation. Most relations. Well,
To prove that it isn't, we just have to prove that one of them is false.
one of them is it. So on your next homework, I think what I will ask you to do is that find the relation that is reflexive, but not symmetric and not transitive. Find a relation that is symmetric, but not reflexive and not transitive. Find a relation that is transitive and symmetric, but not. So how many possible relations you can have? 8. Okay, 8 possible combinations. So for example, yes, no, no, yes, yes, no. Okay,
No, it's. Wait, no.
2, 2, 2.
Yeah,
Right,
no.
2 choices for each.
2, 2.
So you have to find 8 possible relations that are not equivalence relations. That satisfies exactly 2, or exactly 3 of the property. Okay? Or not. Okay? It's a nice one. It's a nice one. You won't have to justify it, of course, because it's gonna take a long time. But yeah. Okay, great. What time is it? Still have 5 minutes left. Oh, still have 8 minutes left. Let's define. We have time for a definition. The equivalence class. So let X, this is the definition. Let X be an X. An equivalence relation. The equivalence class of X denoted X or XR is so what is this? It's the Y in X, right? Such that X is related to Y. Or Y is related to X. It doesn't matter, right? Because in equivalence relation, if Y is related to X, then X is related to Y. Okay, maybe let's do a small example in class. Okay? So I will make a relation on all those who are sitting now and saying that they are related if they sit in the same column. Okay? So if 2 people are seated in the same column, then they are related. Is this an equivalence relation?
Yes.
Think about it. If I'm sitting in the same column as you, then you're sitting in the same column as me. Okay? Now, am I sitting in the same column as myself?
Yes.
So that's the first 2. Transitivity. If I'm sitting in the same column as him, and he is sitting in the same column as her, then am I sitting in the same column as her? That's an equivalence relation. Agreed? Everybody? Should I repeat this? Just nod your head. I'll see it. Should I repeat this?
Oh.
Yes.
Okay. So if I'm sitting, so I'm saying 2 people are related if they're sitting in the same column. Am I seated in the same column as myself?
No, that's time to
If I'm sitting, well, I'm not sitting, but if someone is sitting, yeah, okay, suppose I'm sitting. Am I sitting in the same column as myself? Yeah.
Yes.
Now, if I'm seated in the same column as you, are you seated in the same column as me?
Yes.
Yeah. Now, if I'm seated in the same column as you, and you are seated in the same column as him, am I seated in the same column as him?
Yes.
Yeah. This is clear, right? So this is an equivalence relation. Now, what's your name? Nathan. So the equivalence class of Nathan are all the students who are seated in the same column as Nathan. So all the students who are sitting in the same column as Nathan, could you raise your hands? Yeah? Yeah?
Wish I could pull that together.
Right? This is the equivalence class of Nathan. Okay? Do we see that? What's your name?
Damien.
Damien. So the students in the seated in the same row as Damien, could you raise your hand? Yeah, Damien's here. Yeah. Notice it's the same thing, right? It's the same set of students that raise their hands. You see this? Yes or no? Okay? So let's do a more concrete example, well, a more abstract example. On Z, x is equal to Z, and x is related to y if x minus y is divisible by 3. Okay, let's find the equivalence class of 0. What is the equivalence class of 0? It's all the y's in Z such that y minus 0 is divisible by 3. Agree or not? What are these numbers? Y minus 0 is divisible by 3. What does it mean? It means that y is divisible by 3. Okay, could I, so y and z such that y is equal to 3k for some k in z. We agree or not? Okay. What are the classes of this set? What are the elements of this equivalence class? Someone else? Any volunteer?
Can you repeat the question?
What are the elements of this equivalence class? Is minus 3 an element of the class?
Yes.
0,
Yes.
7,
No.
3.
Yes.
So what can I say? This is just all the multiples of 3 basically, well, of course. So this is minus 3, 0, 3, and so on. Now your friend, I think, suggested that if you take all the integers and you multiply them by 3, you get this set, right? So take 0, multiplied by 3, what do you get? 0. Take 1 and multiply it by 3, what do you get? 3. So this is 3 times 1, this is 3 times 0, this is 3 times 2, this is 3 times minus 1. So what can I say? I just multiply 3 by the entire set of integers. Okay? Okay, what is the equivalence class of 3? Can you tell me what's the equivalence class of 3?
It's the same.
It's the same, right? You see that? We agree? You see that? Okay, great. So equivalence class of 0, and we'll prove this more formally, is equal to the equivalence class of 3. Now, what's the equivalence class of 1? So what is the equivalence class of 1? Is y and z such that y minus 1 is equal to 3k for some k in z. So really, what is that? Is 1 in this set 1 minus 1, is it a multiple of 3? So 1. Then what's the next one? 4. Then what's the next one? 7. What's the one before? 1 minus 3 is minus 2. Now notice, this set, is this set, and you add 1 to every single element. Add 1 to 0, what do you get? 1. Add 1 to 3, what do you get? Add 1 to minus 3. So this is 1 plus 3z. And similarly, the equivalence class of 2 is 2 plus 3. Okay? Great, so we'll call it a day today. I guess I don't have any time left. So see you on